Okay, this is section 15.6, damped oscillations. We've visited this before with the pendulum, the experiment we did with the swinging of a pendulum where we varied the length of the string, the mass, the angle. And then we did a last experiment where we looked at the damping, and sure enough, you could see that with each subsequent swing of the pendulum, that it lost a little bit of its amplitude. That was just natural damping from the internal energy of the string warming up, air resistance, a lot of different factors. And so we're going to study damped oscillations. Back in chapter 6, we discovered resistive uh, forces. One that was proportional to the velocity, and one that was proportional to the velocity squared. When the velocity squared, we introduced a drag coefficient, and in the other, we introduced a coefficient B, and that's the one we're going to be concerned with here. So this is an example of two damped oscillations. One, if you take a spring and you have a mass, but if you recall the FET experiment that we did, if you didn't have any damping, the little oscillator would just go back and forth indefinitely. In order to slow it down, you had to add some damping. Well, that was an idealized case. This is, in most cases, you're going to get damping, and I'm going to have a little video following this section that demonstrates how we use damping in the lab on a triple beam balance. So if you take this mass and suspend it from a spring and get it to oscillate, the viscosity of the liquid will cause the mass to eventually slow down. And here in the right-hand picture, they're showing you the bridge. This is a bridge over the Thames River that when people first started walking on it, well, on the inaugural day, it would sway. It would sway and made people uncomfortable. They closed the bridge for 2 years and added the red arrow points to these masses that they. I'm on the wrong slide. The spring-loaded devices mounted below the bridge are dampers that transform mechanical energy of the oscillating bridge into internal energy, reducing the swaying motion of the bridge. So damping can be you have damping in your car. I mean, if your shock absorbers ever run out, your car will oscillate after going over a bump, and you want to reduce that. So we're going to talk about damped oscillation. The resistive force is equal to minus B times the velocity. This is a throwback to chapter 6. And so the force, I'm going to reduce this so it doesn't interfere with the screen. The Fx is equal to minus Kx. That's just the restoring force from a spring minus BVx, velocity. And that's equal to mass times acceleration. Now, if we throw the mass times acceleration over to the left-hand side and use for the acceleration, it's the second derivative of position, d squared x dt squared. And for the velocity, we use dx dt. You see the mass times the acceleration plus b times v, because we threw it over to the other side, plus kx is equal to 0. Now that's a complicated equation to solve, so we're just going to give you the answer. X is equal to ae to the minus b over 2m times t times the cosine of omega t plus phi, where phi is a phase constant, and omega is defined as the square root of k over m minus b over 2m squared, and it's also equal to omega 0 squared minus b 2m divided by 2m squared. Okay, and this is what the equation ae to the minus b 2m times t. This is what it looks like. The amplitude decreases as AE to the minus B 2M divided by 2M times T. If you plotted the damping portion of the pendulum, you would see a curve that you would have seen a curve that's similar to the dotted line. We were only looking at one side of the pendulum, so we didn't plot the whole thing, but the one side of it did have a curve like this. And this is the equation: x equals AE to the minus B divided by 2MT times cosine omega t plus phi. And then there's different types of damping. You can see that the if V over 2M is less than omega 0, then the system is under damped. You get the blue curve. And if it's what we call B critical, if B critical divided by 2M is equal to omega 0, you get the red curve. This is critically damped. That's the BC equals, it's critically damped. And if BC divided by 2M is greater than omega 0, you get the black curve. In other words, it's a very slow system. It takes it a long time to slow down. So the ideal one, the critical one, is the red curve. And we'll stop there and we'll go on to force oscillations next.